Generalization for lines not passing through the origin. Welcome, everyone. Let's begin our new session on the generalization for lines not passing through the origin. Now, if you recall from our previous lesson, we focused specifically on how to calculate the angle between two lines that pass directly through the origin. While that was a great starting point, we need to address a more realistic scenario. In a three-dimensional coordinate system, the vast majority of lines you will encounter do not actually pass through the origin, which is the point 0, 0, 0. So, the big question for today is, how do we handle these lines? In this subsection, I am going to show you why the formulas we worked so hard to derive for lines passing through the origin are actually much more powerful than they seem. You will see that these formulas are still perfectly applicable to any two lines in space, regardless of where they are positioned in the coordinate system. By the end of this lesson, you'll understand how to bridge that gap. Understanding the concept. The most important principle to grasp here is that the angle between two lines depends solely on their direction, not on their location in space. In other words, where the lines are sitting in the coordinate system doesn't change the tilt or the orientation of the lines themselves. Think about it this way. If you have two lines, let's call them L1 and L2, located anywhere in 3D space, you can actually shift or translate them, moving them through space without rotating them at all, until they both pass through the origin. When we perform this shift, we create these new lines, which we can call L'1 and L'2. Because we only moved them and didn't rotate them, these new lines remain perfectly parallel to our original lines. And here is the key mathematical takeaway. Because they are parallel, these new lines possess the exact same direction ratios as the original lines. So, since the relative orientation, or the opening between the lines hasn't changed during this translation, the angle theta between our original lines, L1 and L2, is exactly identical to the angle theta between our new lines, L'1 and L'2. This is what allows us to use the same formula we learned previously, which we will break down step by step in the next slide. Now that we've established that most lines in 3D space don't actually pass through the origin, let's dive into the core concept that makes our lives much easier. Step-by-step logical breakdown. Now that we understand the concept of shifting lines to the origin, let's break down the actual procedure into a clear, logical process. If you follow these 3 steps, you'll be able to solve any problem of this type. First, your primary task is to identify the direction ratios. You need to look at your given equations for line L1 and line L2 and extract the values for a 1, B, 1, C1, and a 2, B2, C2. Think of these ratios as the DNA of the line. They don't tell us where the line is located, but they define its slope or its specific orientation in 3-dimensional space. Second, we use a technique called assuming parallelism. To make the math easier, we mentally construct 2 auxiliary lines. Let's call them L'1 and L'2. We imagine these new lines passing directly through the origin, but we ensure they are perfectly parallel to our original lines. This brings us back to the familiar territory we discussed in the previous section. Finally, once you have these parallel lines in mind, you can simply apply the cosine formula. Because these new lines share the exact same direction ratios as our original lines, the angle between them is identical. You will calculate the cosine of theta by taking the absolute value of the quantity, A1 times A2 plus B1 times B2 plus C1 times C2, all divided by the product of the square root of a 1 squared plus B1 squared plus C1 squared, and the square root of a 2 squared plus B2 squared plus C2 squared. As we will see in the next few slides, I'll show you exactly how to apply this formula to a concrete numerical example. Real-world analogy. Now, if the mathematical concept of translation feels a bit abstract, let's try a real-world analogy to make it more intuitive. Imagine you are holding 2 pencils in the air, tilted at a specific angle to one another. Now I want you to move both of those pencils, say 3 feet to your left and 2 feet upward, but here is the crucial part. you must ensure that you do not rotate them at all. You are simply shifting their position in space. Even though the pencils are now located in a completely different part of the room, if you look closely, you'll notice that the angle between them remains exactly the same as it was when they were first held. In this analogy, moving the pencils is exactly equivalent to what we discussed in the previous slides. It is the process of translating our lines from their original positions in 3D space back to the origin. This confirms that the angle depends only on the direction, not the location. Now that we have this visual intuition, let's move on to a worked example to see how we apply this logic to actual equations. Worked example. Now let's apply the theory we have just discussed to a concrete problem. Here is our task. Find the angle between the line L sub 1, which is given by the equation x minus 2 all over 2 equals y minus 1 all over 1 equals z plus 3 all over 2, and the line L sub 2 given by x plus 1 all over 1 equals y minus 4 all over 0 equals z minus 2 all over 1. To begin our calculation, we must perform step 1, extract the direction ratios. As we learned in the previous slides, the position of the lines does not affect the angle, so we only need to focus on the denominators. For line L sub 1, the direction ratios are a sub 1 equals 2, b sub 1 equals 1, and c sub 1 equals 2. Similarly, for line L sub 2, the direction ratios are a sub 2 equals 1, b sub 2 equals 0, and c sub 2 equals 1. We will take these specific values and use them in the next steps to calculate the dot product and the magnitudes required for our final formula. Worked example continued. Now that we have successfully extracted our direction ratios from the equations in the previous slide, let's move on to step 2. As we discussed earlier in our concept overview, the actual position of the lines in space doesn't change the angle between them. So, even though our first line passes through the point 2, 1, negative 3, and our second line passes through negative 1, 4, and 2, these specific coordinates are actually irrelevant to our calculation. We can simply apply the generalization we learned by using the direction ratios we just identified directly in our cosine formula. This brings us to step 3, where we begin the actual computation by calculating the dot product of these ratios, which forms the numerator of our fraction. To do this, we multiply the corresponding components of our two sets of ratios and add them together. That is, a sub 1 times a sub 2 plus b sub 1 times b sub 2 plus c sub 1 times c sub 2. Plugging in our values, we get 2 times 1 plus 1 times 0 plus 2 times 1. This simplifies to 2 plus 0 plus 2, which gives us a final numerator of 4. Keep this value in mind, as we will need it for the next step where we calculate the magnitudes. Worked example continued. Now that we have successfully calculated the dot product of our direction ratios in the previous step, we move on to step 4, which is calculating the magnitudes of our two lines. To find the magnitude of line 1, we take the square root of the sum of its direction ratios squared. That is, the square and 1 squared plus 2 squared. This simplifies to the square root of 4 plus 1 plus 4, which gives us the square root of 9, and finally, just 3. Next, we do the same for line 2. We take the square root of 1 squared plus 0 squared plus 1 squared. This simplifies to the square root of 1 plus 0 plus 1, which leaves us with the square root of 2. Moving on to step 5, we can now perform the final calculation to find the angle. We plug our results into the cosine formula. We take the absolute value of the numerator we found earlier, which was 4, divided by the product of our two magnitudes, which are 3 and the square root of 2. This gives us 4 over 3 root 2. To make this look a bit cleaner, we can rationalize the denominator, which results in 2 root 2 over 3. Finally, to isolate the angle theta, we take the inverse cosine of 2 root 2 over 3. This gives us our final exact value for the angle between the two lines. Key takeaways. First, remember the principle of position independence. As we saw in our worked example, it doesn't matter where the lines are located in the three-dimensional coordinate system. The angle between two lines is entirely independent of the specific points they pass through. Whether a line passes through the origin or is shifted far away into space, the angle remains unchanged. Second, always remember that direction ratios are key. When you are faced with a problem like the one we just solved, your primary focus should be on extracting the direction ratios, such as a sub 1, b sub 1, c sub 1, and a sub 2, b sub 2, c sub 2. These ratios, or the direction cosines, are the only pieces of information you actually need to find the angle. The coordinates of any point on the line are, for this specific calculation, completely irrelevant. Finally, keep the translation principle in mind. This is the logical foundation of everything we've discussed. You can mentally or mathematically represent any line in space as a parallel line that passes through the origin. By performing this translation, you can use the standard cosine formula, where the numerator is the absolute value of a sub 1 times a sub 2, plus b sub 1 times b sub 2, plus c sub 1 times c sub 2, all divided by the square root of a sub 1 squared, plus b sub 1 squared, plus c sub 1 squared, multiplied by the square root of a sub 2 squared, plus b sub 2 squared, plus c sub 2 squared, to find the angle with total confidence. Now that we have worked through that practical example, let's pause and summarize the most important points from today's lesson to ensure you have a solid grasp of this concept. In our next session, we will look at some common pitfalls to avoid, so make sure you have these core principles internalized. Common mistakes. First, let's talk about using coordinates instead of ratios. This is perhaps the most frequent mistake I see. When you look at a line equation, like the one we used in our worked example, you'll see specific points, such as x minus 2, y minus 1, and z plus 3. It is very tempting to plug those numbers, the 2, the 1, and the negative 3, directly into your cosine formula. But remember, as we discussed in the earlier slides, the position of the line doesn't matter, only the direction does. You must extract the direction ratios, the a, b, and c values, and use those instead of the position coordinates. Second, please be careful not to ignore the absolute value signs. In our formula, you'll notice those vertical bars around the entire fraction. When we calculate the angle between two lines, we are generally looking for the acute angle, which is the angle between 0 and 90 degrees. For the angle to be acute, the cosine value must be non-negative. If your calculation results in a negative number, the absolute value will flip it to positive, ensuring you get the correct acute angle. Finally, don't let the concept of intersection confuse you. A common misconception is that two lines must actually touch or intersect to have an angle between them. However, in three-dimensional space, we have something called skew lines. These are lines that are neither parallel nor intersecting. Because of the generalization principle we learned today, we can still find the angle between these skew lines just as easily as any other. As long as you have the direction ratios, the formula works, regardless of whether the lines meet in space. Now, before we wrap up today's lesson, I want to pause and highlight a few common pitfalls. As we've seen throughout this tutorial, the math itself is straightforward, but it is very easy to trip up on the details. Keep these points in mind, and you'll avoid the most common errors in your calculations.